Hey guys, welcome to today's class. Have fun.
So today we'll be looking at light waves. We're looking at reflection of light waves on plane mirrors. Also looking at the applications of plane mirrors using the principle of reflection. So in the last class we talked about waves. Talked about the types of waves, mechanical waves, electromagnetic waves, their properties and types. So today we'll be looking at a type of electromagnetic wave, which is light wave. A light wave are disturbances which travels through material mediums or they require no medium for their mode of propagation. So light wave travel through vacuum since it is an electromagnetic wave. So today we're looking at the properties of light waves and the characteristics and application of various forms of light properties. Okay. So firstly we'll be looking at sources of light. Now, what is light in itself? The origin of sensation or vision is what referred to as a source of light. Now, light emanates from a particular point. Now, light emanates from a particular source, spreads out before we can see with our human eyes. So, light is the perception, is the source of the perception of vision. He says here that the origin of sensation of vision is a source of light. So a light ray is produced from a particular source, and we have various sources of light. So we have luminous objects and non-luminous objects. Now, by luminous objects, we mean points or sources of light which are natural or they are man-made. When we are talking about luminous objects now, these are objects which can produce light, luminous. But for non-luminous, they can't produce light. Instead, for non-luminous, they only reflect light which falls upon their surfaces. So for luminous objects now, these are objects or materials which produce light rays. So natural sources of luminous rays, we have the sun, we have the moon, and we also have some animals or insects which can also produce light rays. We have fireflies, we have glowworms. So these are origins of light, origin of sensation, of vision. So we also have man-made luminous objects. For man-made luminous objects, these are objects made by man, as the name implies. For example, we have torch, we also have candle, and various forms of electrical appliances, electric light appliances, like you have the lamp, you have the electric bulb, so on and so forth. So look, these are all classified as luminous objects, sources of light. So also we have non-luminous objects. These objects cannot produce light, but instead they can reflect light from its origin to other surfaces. So a non-luminous object, you have a source of light, and this is the luminous object. Luminous object is a source of light, and this is a non-luminous object. Now, the only function of a non-luminous object is to transmit light from the origin to other points. So it can either transmit, okay, so we see the three types now. We have transparent, we have translucent, and we have opaque. Now, for a transparent luminous, non-luminous object, this is an object in which one can see through it and light can also pass through it. So for a transparent luminous object now, so you can see through it and light can pass through it. So if this is a transparent object, so our light rays can pass through it, and also we can see through the surface of the material. So if, for example, we have a ball here. Now the light rays passes through. The light ray can pass through it. In the same manner, we can also see through it from this particular point and see the ball particle here. So for a translucent object, now we cannot see through it, but light can pass through. Now, a translucent object is an object in which light rays can pass through them, but we cannot see through them. So an example of transparent objects are white nylon, some forms of glasses, some thin clothes materials. Light can pass through, like a white nylon material. Light can pass through and we can also see through it. Examples of translucent objects, we have tinted glasses now. For tinted glasses, light rays can pass through it into the surface in which the glass is used to barricade, but you can't see through it. So that's for translucent. The last category there is the opaque. Now for opaque, we can't see through it, and also light cannot pass through an opaque object. An example of an opaque object is a human being or a wall. So for a wall now, light can pass through it, and also you can't see through a wall. So that's that on sources of light and luminous and non-luminous objects. So quickly, we also have a ray of light. Now what do we mean by a ray of light? Now the direction or path through which light energy travels is what we refer to as the ray of light. Like I said, in this system, you have a source of light and you have the path through which it travels. Now the path through which light travels is what we refer to as the ray of light. And this is a ray. This is also a ray of light, and also this is a ray of light. So a ray of light is the direction or path through which light energy travels, whereas a beam of light is the collection of rays of light. So when we say a ray of light, the simple path through which light energy travels. Now the collection of light rays is what gives us a beam. Now a beam of light is the collection of light rays. So we have different types of beams. We have the convergence beam, we have the divergence beam, and we have parallel beams. Now the study of light energy is very practical in nature. So that's why in most cases, for this aspect of the subject, this is mostly treated in the practical aspect of physics exams. So when you are going to be, when you are sitting for your exams, there's a very high probability that you will meet a practical question on light waves, sources of light and applications, because it's a very practical aspect which you see every day of our lives. So back to the class now. For a convergence beam now, like the name implies, it converges. And when you see something converges, you have something moving towards a point, and the ray of light is moving towards this point now. And this is a convergence beam. These are produced from large sources and they meet at a point to form a convergent beam. Now for a divergent beam, they are produced from a particular source and they emanate outside. So you can see there's a difference between these two. This is a convergent beam. It converges at a point, meets at a point, whereas this is a divergent beam. It's spread out from the source. Then lastly, we have a parallel beam. It's a parallel beam. Now when we get to the rectilinear propagation of light, you will see that light's energy can also travel in straight lines. So a parallel beam are rays of light which are produced in straight lines. So quickly we'll be looking at the properties of light. Light has five basic properties which are categorized as rectilinear propagation, reflection, refraction, diffraction, and polarization. Now in the previous class in which I discussed about wave, Now you can see some of the properties here belong to wave also. That's because light is also a form of wave. In this case now it's an electromagnetic wave. So quickly I'll be looking at the properties of light, but it's a bit similar to the properties of wave, in which I explained in previous classes when discussing the topic wave motion. So rectilinear propagation of light. So for rectilinear propagation, the name implies rectilinear. This is the process in which light travels in a straight line. So in a simple experiment now, it's a source of light. You have a hole here and a hole here. Now, from the experiment, it's seen that light rays travel in straight lines. Example is you have a wall now. Now a wall is an opaque object. Light can pass through it. But if you have a wall now and you make a hole here, now say you use a nail to puncture a hole through the wall now. Now in the first instance, when you put or reflect a source of light here, the light can't pass through it, you can't see through it. But for a wall now that has a particular hole now, it can be observed that on applying a source of light now, you can see that the light ray passes through that tiny hole, comes outside, that is, travels in a straight line. So rectilinear propagation of light simply tells us about the property of light to travel in a straight line, and the experiment which brings this into play, the ray box experiment. So light travels in straight lines. So also you have reflection. Now talking about reflection, I'm talking about the ability of light waves to be incidented at an angle and reflect back at another angle. Now what does this simply mean? You have a source of light. Now this light wave travels, it hits an obstacle with a particular angle to the obstacle, and also bounces back and continues with an angle. So the angle here is known as the angle of incidence, and this is the angle of reflection. So the ability of light waves now to be incidented at a particular angle and bounce back is known as reflection. So reflection is the propagation or the change in direction of light waves when they hit an obstacle. Now for refraction now, let's say refraction is the ability of light wave to be propagated from one medium to another. Now in the case of reflection, talking about it hits an obstacle and changes direction, it is being reflected. Now for propagation now, I'm talking about the ability of the light wave to travel from one medium to another. Now this light wave passes through this medium. Now light waves coming from air now passes through glass. Glass can transmit light waves. It is a transparent, it can also be a translucent object. So the ability of light waves to move from one medium to another can have air to glass, water to air to water, glass to air, etc. So light wave can travel from one medium to another. Now the extent of this travel or this propagation determines on the property of the material in which the light waves pass through. So that's refraction. Now for diffraction, it is the ability of a light wave to continue its propagation through an opening along its path of propagation. Now same way with the way waves also diffract. Now using this example of a wall without an opening and the one with an opening. Now light waves passes through this opening. Now you can have a beam of light coming to this tiny opening. So the light waves begin to diffract. That is the ability of the light wave to continue its journey because of an opening in the obstacle. For reflection now, you don't have any opening. It's just it's the obstacle, bounce back, continue its mode of propagation. Now for diffraction, meeting an obstacle now, but it encounters a hole in the obstacle now. So it's able to bend through the obstacle and continue its mode of propagation. So it somehow like converges now. It tries to converge to this point, passes through the obstacle and begins to diverge outside. So the mode, or the higher the energy of light, the higher the diffraction. So for a small hole now, the amount of energy which will be diffracted will be smaller because of the wavelengths be shorter. But for a larger light beam now, larger light energy now, meeting a larger hole, or for light energy encountering a larger hole or slit. So for light energy traveling in small holes now, the diffraction is larger after coming out of the hole. But for a larger hole now, it takes almost all the beams of light to pass through. So the diffraction rate is much lower compared to a very tiny hole. So also you have polarization. Now by polarization, it is the ability of light wave to be able to confine and get adapted to any opening along its paths of propagation. Now polarization is the confinement of light waves to travel in a straight line. So it's a bit similar to when we refer to as rectilinear propagation of light. So for polarization simply talks about the ability of light particles to travel in straight lines. So on encountering any opening now, any obstacle, for obstacles it reflects because there is no opening for the light wave to continue propagation. But on encountering obstacles now, the ability of light wave, to move in a straight line and continue its mode of propagation is what referred to as polarization. So there is a phenomenon referred to as plane polarization of light. So next we have magnification. Now we have, due to the ability of light wave to travel from one medium to another. In this case now we'll be looking at plane mirrors. Say reflection on plane mirrors from the topic. So a plane mirror is a simple medium made of glass, plain glass mirrors now, in which light particles can either reflect or refract through it. Now we have a plane mirror. We also have a lens. Now there is a difference between these two, in the sense that for plane mirror now, plane mirror reflects light. Now this is the coated surface. Plane mirrors reflect light waves. So on incidenting light waves here, they begin to move in another direction. Now for lenses lenses refract light rays. So a plane mirror reflects while a lens refracts. So for a plane mirror, you have light waves incidented at it. But for a lens now, you have light waves being refracted through it. So that's the simple difference between a mirror and a lens. But for now, we'll be looking at reflection of plane mirrors. Now, the magnification of a mirror is referred to as the ratio of the image distance to the object distance, or the ratio of the image height to the object height. So that's why I use distance synonymous to height. So when we talk about magnification now, the ratio of the image distance now, this is the image distance I. Image distance over object distance is equals to image height over object height. So you have a mirror now which you want to use to see through an object. Now you have the distance of the object from the mirror, which is object distance, and the object has its height, the height of the object. Now the reflection of this image now on the mirror. For the reflection of the object on the mirror now, you are trying to see through this mirror to locate the position of a human standing on. So the object has its height, it has the distance from the mirror. So the reflection also gives us a new image height. Okay, that's image height, and its own distance also from the mirror. Object height, so image height. So you have the object height, the object distance, and you have the image height and the image distance. Now, sorry for the image distance. So the relationship between the image distance over the object distance and the image height over the object height gives us the magnification of the mirror or the lens. So magnification is simply the ratio of these relationships now. So the relationship here is referred to as the magnification. And further classes, as the class move on, will be seeing how to apply this formula in solving questions on light waves. So in continuation, I'll be looking at reflection on plane mirrors now. Now I've explained earlier that mirrors reflect light waves while lenses refract light waves. So by reflection now, we simply mean the repropagation of light waves when incidented at a particular angle on a plane surface. Now this is what I explained here on reflection. Now it says repropagation of light waves when incidented at a particular angle on a plane surface. Now you have a plane surface now. This case is a mirror. Now the repropagation of wave when incidented. So you can also have normal. You have a light wave. You have a light wave. This is a surface now. You have a light wave incidented with a particular angle, which is known as the angle of incidence. And it is reflected also with an angle known as the angle of reflection. So reflection is simply known as the repropagation of light waves when incidented at a particular angle on a plane surface. Now, the surface now determines the mode of repropagation. Now you can have a smooth surface. You can have a rough surface also. And for a smooth or regular surface now, you have two types of surfaces now. You have the smooth or regular reflection due to a smooth or regular surface. Now, when light rays are reflected on smooth surface, the rays are known as a regular ray. So the rays formed after reflection on smooth surface are regular rays. Now you have a ray of light. This is a smooth surface, continuous. You have another ray of light. Smooth surface is continuous. So these are regular light rays. But for a diffused or rough surface now, okay, this is a smooth surface. This is a rough. Now, rays of light incident here, move. Another ray of light incident here, move. So you can see the point in which this incident is different from the height here now, because you have a difference in height. So a ray of light which gets incidented here moves with a different angle from a ray of light which is incidented at this point. But for a smooth surface, at any point in time in which the ray of light is incidented, they move, or sorry, they reflect with the same angle throughout. But like I explained here, for rough surfaces now, because they have different height levels now, the ray of light incidented here, another is incidented here. They are at different height levels now. So the mode of reflection is definitely different. So for a smooth surface, we have regular rays. For a rough surface, we have irregular or diffused reflected rays. Now we have laws of reflection. We have laws that guide the reflection of light waves on surfaces. So basically, we have two laws associated with reflection. And the first law states that the incident ray, reflected ray, and the normal ray all lie on the same plane. And this is an example which I have done here. This now. So we draw for us to see. It says, and this is the normal. It says the incident ray, the reflected ray, and the normal. This is the normal. They all lie on the same plane. This is our plane OA, and this is our normal, and this is our incident ray now. It has its own angle of incidence I, and this is our, on hitting this surface, it reflects with another angle R and continues its mode of propagation. So the first law of reflection states that the incident ray, reflected ray, and the normal ray all lie on the same plane. So our incident ray, reflected ray, and the normal, they lie on the same plane. And this is the first law of reflection. Okay, so the second law of reflection states that the angle of incidence is equal to the angle of reflection. Okay, you have an obstacle, light rays being reflected, incidented, reflected, and the angle the angle with which this light ray is being incidented, I, is equals to the angle in which it will be reflected also. So in this instance, the second law of reflection states that I is equals to R, which means that our angle of incidence is equals to the angle of reflection. So in analyzing this simple diagram now, we have our angle of incidence I, angle of reflection. Now we also have two other angles here, and this is referred to as the angle of glance, G. So we also have an angle of deviation, which is known as D. Now if this incident ray was said to pass through this medium and continue its mode of propagation, which is refraction, so it will be said to have moved with D, which is known as the angle of deviation. Now our angle of deviation is equals to 2G. So this is the relationship which exists between the angle of deviation and our angle of glance. So in summary, since this is a straight line, and the sum of angles on a straight line is 180 degrees. So we can say the angle of glance plus the angle of incidence plus angle of reflection plus the angle of glance is equals to 180 degrees. And we also have another expression, which is the angle of deviation is equals to 2 multiplied by the angle of glance. So if, for example, you have an angle of incidence of 30 degrees, so automatically our angle of reflection also will be 30 degrees. So and if this is 30 degrees and this is 30 degrees, so the sum of these two gives us 60 degrees. So the sum of angle on a straight line is 180. 180 minus 60 gives us 120 degrees. So meaning angle of glance should be 60, and this was 30, this was 30. So that gives us 180. So if our angle of glance is 60 degrees, so our angle of deviation automatically becomes 2 multiplied by 60, which gives us 120 degrees. So this is a simple relationship which exists between the angle of incidence, angle of reflection, the angle of glance, and the angle of deviation. So quickly now, we'll be looking at locating images on plane mirrors. So like I said earlier, you have a plane mirror now in the table. This is a plane mirror. Now a plane mirror reflects light waves. Now it can't refract a plane mirror because it has one surface coated. It has two surfaces, and one surface is coated while the other surface is plain glass, which the light waves can incident, reflect, incident, reflect, incident, and reflect. So if you have a pin now, and this is a simple experiment, you have a pin in front of this plane mirror. Now you know this is our object now. So this is our object distance now. This pin has height, object height. Now to locate this pin, now looking from this side now, I want to locate the positioning of this pin. So we use what we call a search pin. Now a search pin will be placed here. Now because this pin is at the front now, we place a search pin behind now, trying to find the reflection of this pin. So it's something like this. You have a pin, you have a glass in front, and this pin is in front of the glass. Now in order to see the reflection of this pin from behind, now you are standing at the back of the glass, standing at the back. To see the reflection of this pin in front, you use a search pin to find the reflection. Now you place the search pin here, you see you can still find the pin. Now you place the search pin parallel to the positioning of the object here. So this search pin now is what gives us the image distance and the image height. So when placing a search pin, we follow the principle of reflection to locate the position of images formed behind a mirror. Like I said earlier, mirrors reflect light waves. So in doing this simple experiment, we have some terms which we encounter. And first is parallax. And what do we refer to as parallax? Parallax is the deviation of the image formed as a result of improper placement of the search pins. So when carrying out experiments on lights, now the most common type of error which will occur is known as parallax error. Now what do you mean by parallax error? Now you have a pin already standing, you have a mirror. Now you want to look through the glass to find the location of the pin. Now because of errors, inaccuracy now, and the pin had an image, an object distance and object height. In searching for this pin now, you notice that the image height and the image distance will be different from the object height and object distance. Now this difference in results is due to parallax error. So the deviation of the image formed as a result of improper placement of the search pins is what referred to as parallax. So we also have what we refer to as lateral inversion. And the property of a plane glass which differentiates it from mirrors is what we refer to as lateral inversion. Now for lateral inversion, you have an object now standing in front of a mirror. This is a mirror. Now this is the right and this is the left hand. Now the reflection of the object in the mirror shows us the left and the right. And this is what referred to as lateral inversion. So it's a property of plane glass which differentiates it from mirrors or lenses. And because plane mirrors just do the reflection, they reflect the image. Sorry, they reflect the object now in the mirror as the image. And when you look through a plane mirror now to look at yourself, so it reflects the objects in the image. So as a result of that, there is a phenomenon referred to as lateral inversion, in which what you see is opposites of what you are facing. So in the case whereby your right hand and your left hand, so in the mirror now, because of the inversion of the image now, you have your left hand at this side and the right hand at this side. So this is simply due to reflection of light waves. So we have images formed on plane mirrors. And for images formed on plane mirrors, the image size is always equals to the object size. The image size is always equals to the object size. You have the height. The size of the objects should always be equals to the size of the image in plane mirrors. And the image distance is also equals to the object distance in plane mirrors. Now the images are laterally inverted and they are virtual images. Like I explained earlier, you have lateral inversion, the object height equals to image height, the object distance is equals to the image distance, and you have virtual images being formed on plane mirrors. So also we have images produced on inclined planes now. Now you can have a mirror, have images produced on inclined plane. You can have a mirror in which light is being incidented and reflected. But what happens when we have groups of mirrors now incidented at different angles? And you have this incident ray. So for a group of mirror, we have a simple formula which relates them. So it gives us the number of images. So for group of mirrors incidented at different angles, the formula which enables us to know the number of images which we'll be expecting is this. Now if you have two mirrors now incidented at two angles to each other, to one another now, let's say they are incidented at 60 degrees to themselves now. So this is 60 degrees. And the number of images formed represented as 360 over theta minus 1 would simply be 360 over 60 minus 1. So it gives us 5. So the reflection of this image will be in 5 places. So this is what we see when we enter malls with numerous glasses now. Now you see, standing in front of different arrangement of mirrors now, you have different arrangement of mirrors with different angles to one another. You see multiple images of yourself. So this is as a result of this principle. So the number of images formed is equal to 360 divided by the angle in which the mirrors are inclined to one another minus 1. So lastly, we'll be looking at the applications of plane mirrors. Now plane mirrors are applied in two simple what would I call them? Two simple two simple tools for seeing: light tools, vision tools, or vision equipment. First of all, we have the periscope. And the periscope enables one to see over walls and obstacles. The principle is based on the reflection of rays. And you have a man standing here, and this is a wall. Now you can't see a fish now at this point now because it's over the wall. Now by using a periscope can enable the man to see over this wall. So because this is the line of vision of the man, a tree standing here now, this is a tree. The man can't see this tree because of the height difference. Now a periscope comprises of two glasses which are incidented at angles to themselves now. So you have a man standing here. Now using a periscope, you have the tree here now. So the periscope has a glass, a mirror here. It has another mirror here. So a man looking through a periscope now, the light wave from this tree transmits to this point and is being reflected down and reflected to the man's eye. So the use of a periscope enables a man to see over obstacles using the principle of reflection. The light waves being incidented are being refracted, incidented back. So it's a simple principle of light waves which is due to reflection. The incident wave being reflected here to another mirror and also incidented back to the viewer. So also we have a kaleidoscope. Now a kaleidoscope is two mirrors placed at angles to one another. So a mirror placed at various angles to each other is known as a kaleidoscope. The kaleidoscope uses this principle of images produced on inclined planes. So if a kaleidoscope is placed at, let's say, 40 degrees to one another, mirrors placed at 40 degrees to one another, the number of images which will be formed by that kaleidoscope will be 360 over 40 minus 1. So that will give us 9 minus 1. Give us 8 images which will be produced. So lastly, we'll be looking at applications of plane mirror. Now, plane mirrors are used in production of viewing glasses or dressing mirrors. Mirrors in which we used to see ourselves. Simple reflection. Look at the mirror and you see the reflection of yourself in the mirror. Used in making periscopes. Periscopes are used to see over walls and obstacles. Now using sextant device. Now this is a navigating device. You have a kaleidoscope and you have illusion images. So plane mirrors and the principle of reflection works hand in hand. So in the next class we'll be looking at refraction now, refraction through material mediums, and we'll be looking extensively at calculations because basically this is more practical when practicals are being carried out. So the knowledge of light waves will enable us to excel in our physics practicals. But from the next class, we'll be looking at some theoretical and calculation aspects of light waves, looking at refraction, looking at lenses and how light waves reflect and refract through lenses. Thanks for listening.
I hope the class was interesting. If you have questions, please drop them in the comment section or send us an email. We will love to help you further. See you in the next class.